Welcome to section 3.3, where we are going to talk about the dimension of a space or subspace, and also introduce a theorem called the rank nullity theorem. So a subspace can be the space itself, which is why we're going to think of examples as R2 and R3, for example. We all have an intrinsic understanding of what the dimension is. If we talk about the plane R2, it has 2 dimensions, and if we look at space R3, it has 3 dimensions. But here's how we would define the dimension mathematically. Consider a subspace V of Rn. The number of vectors in the basis is what we call the dimension, and it is written dim V. So here's space R3, we have the standard basis E1, E2, E3, and with these 3 vectors we are able to reach everywhere in space. This means that E1, E2, and E3 are spanning the space. Moreover, none of these 3 vectors is redundant. I could not remove E1 and still go everywhere. I could not remove E2 and still visit all of space. I could not remove E3 and still visit all of space. So none of these is redundant, and they are enough. So they span R3, and this is why, because there's 3 of them, we say that R3 has 3 dimensions. You could choose another basis of R3. This is the standard basis, it's the easiest one, but you could choose other vectors in R3 that also span all of the space. You can think about E1, E2, E3 as any vector in R3 is a linear combinations of those. So the vector, for example, 4, 5, 2 is a linear combination of these. It's 4 times E1 plus 5 times E2 plus 2 times E3, 4, 5, 2. But you could choose 3 different vectors and still find a linear combination of these 3 vectors that would create the vector that you're studying. In that different dimension, it would not be 4, 5, 2, but it would be geometrically the same one. So the standard basis vectors are E1, E2, E3 in multivariable. We call them ijk for R3, but when we have n dimensions, it's more convenient to use this notation. So a theorem, which is worth really thinking about and trying to make sense of each of these sentences. Consider a subspace V of Rn with dimension m. So m is necessarily less than or equal to n, since we are living in the space Rn. A subspace could not have a dimension that is more than n. But let's focus on this notion here, that we are in a space or subspace that has m dimension. There are at most m linearly independent vectors. So we cannot find an extra vector that is more than the dimension that would remain linearly independent from the others. We need at least m vectors to span V. These 2 things together actually mean that the basis is m for a subspace of dimension m. If m vectors in V are linearly independent, then they form a basis. If m vectors in V span V, then they form a basis. All of these kind of tie the knot together that you need exactly m vectors, no less, no more, to span a subspace of dimension m, and that they can be linearly independent, and they need to be linearly independent to be a basis. Alright, now we are going to look at a big exercise. This matrix is exactly the same as the matrix on page 3, and the questions we are going to do, we've already done on page 3. This is just another way, in particular for the kernel, to find what the kernel of a matrix is. So find the basis of the kernel and what is the dimension of the kernel. So how many vectors are there in the basis? So this is really easy. Once we found the basis, we just count how many there are. So there's two ways to do this exercise. The first one is what we did on page 3. We used RREF, and then we gave names to the free variable. We said that x2 was equal to r, x4 was equal to s, x5 was equal to t, and we were able to express the other ones, x1 and x3, in terms of RST. Here we are going to look at the same problem, but a little bit differently. The answer is going to be the same, obviously. So remember, the kernel is constituted of all the vectors x1, x2, x3, x4, x5 in R5, such that a times vector x equals 0, 0, 0, 0. So the solutions are the same to ax equals 0 if we solve RREF of a times x equals 0. And why is that? Simply because to find RREF equals RREF of a, we use row operations on the matrix, and the row operations, if you think back to the equations themselves, do not change the solution to a system of equations. So this is what we already got on page 3 as well. We just are now going to diverge in the way we solve the problem. On page 3 we said that x2 was equal to r, x4 was equal to s, and x5 was equal to t, and then expressed x1 and x3. Here we are going to look at the columns and notice that every time we don't have a leading one, like in column 2, it means we are able to express this vector using the previous ones. So instead of naming the columns of this matrix a vector a1, vector a2, vector a3, like this would be vector a1, vector a2, vector a3, vector a4, we're going to call these b1, b2, b3, b4, and b5. So b2 is equal to 2 times b1. b3 has a leading one, so we cannot express it in terms of the previous columns, but b4 can. b4 is equal to 3 times b1 minus 4 times b3. It's 3 times this vector minus 4 times that vector. And b5 is negative 4 times b1 plus 4 times b3. So these are the three equations. What that means is if I move the 2b1 to the other side, we would get negative 2b1 plus b2 equals 0. But what that means is that if I placed the vector negative 2, 1, 0, 0, 0 here, I would necessarily get the 0 vector. Negative 2 times 1 plus 2 times 1, and then all the zeros, that is equal to 0. So negative 2, 1, 0, 0, 0 is in the kernel of A. And likewise, using this equation, we can say that it's negative 3b1 plus 4b3 plus b4 equals 0. And what that means is that if I place the vector negative 3, 0, 4, 1, 0 here, and I multiply RREF of A times that vector x, I will get 0. Check if you want. But this is confirming that that vector we just found is in the kernel. And finally, we can do the same with this equation. 4b1 minus 5b3 plus b5 equals 0 gives us the vector 4, 0, negative 5, 0, 1, which, if placed here, would yield 0. So it's also in the kernel. So as a conclusion, we can say that the basis of the kernel of A is these three vectors. They are necessarily linearly independent because each of them necessarily adds a new vector. As you can see, we're going column by column. So for this equation, we had b2. For this equation, we had b4, which we had never had before. And here we have a b5 that will be introduced in the equation. And b5 never showed up before, so it has to be linearly independent from the previous ones. We could also say, in a different setting in a different question that the kernel of A is equal to the span of these three vectors. But now we can answer the other question, since we know this is a basis of the kernel, that the kernel has dimension 3. What about finding a basis of the image? Well, let's remember that the columns of A always span the image. So here we have 5 columns, so these 5 vectors certainly span the image of A. But they are not a basis if some of them are redundant. Everything we found here about the columns B1, B2, B3, B4, B5 is also true about the columns in A. Think about that for a moment. But it comes from the fact, again, that we got RREF of A using a elementary row operations, so it cannot have changed the facts about the columns. So now that we change these B2, B1, etc. to A2, A1, etc., we can see how A2, A4, and A5 are redundant, because we are expressing them with the previous columns. Check if you want that A5 is equal to -4A1 plus 5A3 using these columns, and convince yourself that that is true. So now we have 3 vectors. We have shown that A2 is redundant because it's a linear combination of A1. A4 is redundant because it's a linear combination of A1 and A3, and same for A5. Therefore, we are going to remove them, and the non-redundant vectors are just A1 and A3. So a basis of the image of A is A1 and A3. Be careful, a common mistake is to use B1 and B3 as a basis of the image, but just look for 1 second and you'll see it's impossible. B1 and B3 do not have any values in the 3rd and 4th row. So whereas A1 and A3 do. So it would be impossible to reach everything if we used columns of RREF of A. We do have to use columns of A for the image. And what is the dimension? It is 2, because we just have 2 vectors in that column. So while I'm here, I'm just going to comment on something that's going to come on this next page, the rank nullity theorem, that to find the kernel of A, we used columns 2, 4, and 5, columns where there was not a leading one, and then to find the image of A, we used columns where there was a leading one, so columns 1 and 3. So we can see how the dimension of the kernel, which is 3, plus the dimension of the image, which is 2, always adds up to M, to the number of columns in the matrix. So a quick reminder how to find the image of A. You pick the column vectors of A that correspond to the columns of RREF of A containing the leading ones. And we do need to pick columns of A, not the columns of RREF of A. So, rank nullity theorem, here it is. The dimension of the kernel plus the dimension of the image is always equal to the number of columns in the matrix. So in the example above, it was 3 plus 2, and that is equal to 5. The word rank refers to the dimension of the image, and the word nullity refers to the dimension of the kernel. Okay, let's see an example geometrically of dimensions of kernel and image. If we consider a simple orthogonal projection onto a plane V in R3, so think of all the vectors in R3 and you all project them on one plane in R3. What are the dimensions of the image, and what is the dimension of the kernel? For the image is the plane. It is possible for any vector in that plane. You can choose a vector in R3 and it will be projected on the plane in that location. In fact, you have infinitely many options. So, because it's a plane, it has 2 dimensions, so the dimension of the image is 2. What is the dimension of the kernel? This is a nice exercise to think about. We are looking for vectors such that when you proceed through this linear transformation, you will get vector 0. That's the definition of the kernel. So what are the vectors which, after being orthogonally projected on the plane, will give you vector 0? The answer is it's all the vectors that are perpendicular to the plane. And so we can say that it is the line perpendicular to the plane. All the vectors are on this line that is perpendicular to the plane. So what's the dimension of this line? It is 1. And now we see we can make a simple application of the rank nullity theorem that 2 plus 1 equals 3. Vectors v1 through vn form a basis of Rn if and only if the matrix made of these vectors is invertible. That is, there's just a few steps. So if v1 through vn form a basis of Rn, that means that every single vector b is reachable uniquely. It is possible to express it in terms of v1, vn because they span the space, and since there's no redundancy, there is only one way of expressing b. So b is equal to x1 v1 plus x2 v2 plus xn vn uniquely. There's only one list of x1, x2, x3 that achieves that. This can be rewritten like that. And now we notice, referring to section 2.4, that this matrix is invertible. So look at 2.4 to see where we actually explained that step. Okay, as before, we have a list of things that we've seen until now of all statements that are equivalent. If one is true, then all the others are true as well. Thank you for listening. Thank you for your attention in these difficult sections.